So, yeah, thank you very much, Yuhui, for the warm introduction. I have prepared the presentation that I called New Trends in Facade Modeling. There was an alternative title for it. I wanted to call it The End of Parametric Modeling, but I decided to go with a more traditional name. Yes, it's true, I'm an architect and I was working at Facade for some time. I was working at RFR in Europe and in China, and I had my own office and worked at Friedemann, and now also work at Gartner again in Germany. I'm leading the computational design team, computational design and software development. So we develop digital tools that allow us to perform facade preparation of fabrication data, essentially. So let's see what this is. In the beginning, I will go back a little bit into history and also ask about our processes. Like everybody else in the industry, we have to save money a lot, and we're facing a situation where we just have to become much more efficient than we were in the past. And this applies to everyone, so also to us. So we have to ask ourselves whether we can improve the ways we are working. In 3D modeling, things became quite complicated in the last years, last decades actually. That's kind of historic, and I want to go a little bit into this for now, and then talk about how we react to this. It becomes quite obvious that even though I'm an architect, I'm a very technical person. I'm always running 3D modeling teams, and this is what my interest is, and this is where I can apply myself best. So this will not be so much about architecture and about fancy designs, but a little bit more about the technical aspect of how to make them work. Okay, so how did things get so complicated, and what can we do about it? In the beginning, why do we model at all? We have always colleagues that say, well, why is it even necessary to do so complicated 3D models? Can't we do that in 2D as well? There are still some of them around, but of course, obviously, with the crazy shapes, also very appreciate the previous presentation. We have seen, of course, how the digital tools are properly applied at Zaha Hadid's anyway, and the previous presentation also brought the point home how necessary it is to have proper 3D modeling technologies. Gartner, for instance, these are some Gartner projects that we did in the past decades. Gartner is a company that is more than 150 years old and is very, you could say, unitized curtain wall is something that they helped develop very much after the war. And later on, they went on to do these very, very complex projects together with very interesting architects. And of course, nothing is possible if you don't have very good digital tools and a very good control over digital tools. If we talk about it, we talk about parametric modeling, and we will speak about CATIA a little bit. Here you can see Frank Gehry, who just passed away some weeks ago, and the Fondation Louis Vuitton. That's also a project where I met Yuhui pretty much, and our history goes back to this project a little bit. RFR and Tess, Tom Gray, who also was speaking yesterday, was involved with this project as well. And for this project, they used a software that was pretty new in architecture back then, called CATIA, developed like long time ago already. Here you can see a very historic picture from 1978, which is almost 50 years old. One of the first modeling softwares, or CAD software systems, and it was developed in French military corporation that is building aircraft called Dassault. And here you can see Marcel Dassault, who gets a presentation of this new modeling system by the young engineers. And this system, called CATI and later CATIA, was developed into the software that later was used by Frank Gehry for the Disney Concert Hall, for instance, and for many projects then later. And the new thing here was that it can do these crazy 3D shapes, contrary to just lines and straight surfaces, what you can see in AutoCAD and so on. And Yeah, maybe one more thing to say. At the core, these software systems are parametric. That means you can build successively parametric big systems of relationships. So if you move one point on the left side, then the whole facade may be changing in the model, and all the parts, if it's done well, then all the parts will also adapt automatically all the way down, which is the foundational idea of the parametric modeling. And this is very, very powerful and also quite complex to operate. And but we do that anyway, and here we can see a project that I have been involved in myself in Gartner, in Shanghai actually. The project is in Kowloon in Hong Kong, West Kowloon High-Speed Rail Terminal it is. And you see that there's no 90-degree angle. And there are many little stories here. One of the interesting things was that there was indeed a team of CATIA users, 3 people, and the management was thinking that these 3 people can take care of it because parametric modeling, that's very powerful. But of course, it was not like this. We used a similar software, we used Inventor later, and we had a team of 30 people who do the 3D modeling, and then we had a team of 60 people on top of that, that was turning the 3D models back into 2D drawings for the project because the contract was written like this. Yeah, okay. So things get out of hand quickly, and you may think you have a great software system, but you still need people to operate it, and the work is actually quite significant. Yeah, one more picture from this. My team was always making these generators, and then the other team was applying the generators, and the next team was cleaning the result, and then the subsequent teams were doing 2D drawings from this. All right, and it is this complicated, and we need this many people. So is there a way to do this in a simpler way? And the one thing that we witness in our office and now in the past years is that with much more lightweight software that is per se not parametric, we can achieve almost the same or even better results than with these complicated old parametric modeling systems. In the end of the day, especially in the Western world, I don't know exactly how about China, but in the London market, in the US market, we see that very much. People try to standardize the way we do the 3D modeling, and we go through these phases of the LOD production. So we start very simple, of course, with a wireframe, which is very important and takes a lot of time to get it right. The LOD 100 and LOD 200 use up quite significant amount of time to get it really right before you start everything else, because the whole downstream process depends on it so much. Anyway, the LOD 300 has one purpose. It is the communications model that you use to collaborate with the architect and all the other entities in the process that want to understand what's going on at all, and they want to tune their design and so on. But for us, as the production company, it's not very important to have this model, but we have to have it anyway in order to communicate with the architect. The model that we are really interested in is, I have a laser actually. Yeah, maybe I can see. The model that we are really interested in is the LOD 400 because we need it for the production. That means we will send a LOD 400 model directly to the machines pretty much, and the CNC machines take care of the rest. Of course, there are people involved and it's more complicated than this, but our model is the LOD 400, which we do with CATIA or now with Rhino and use new platforms. And then we always have the problem, how do we actually do the LOD 300 model for the architect? And it's a very painful thing for us because they expect Revit software, and we just not interested in this thing. It is not our core focus to make a LOD 300 model, but we have to do it anyway, and we end up in a situation where we have to model the same building twice, once for the architect so that they can be happy looking at it, and once for our factory who really needs it. Anyway, it's going on. Yeah, and what you have to do is we have to find a balance between complicated and simple. Like for the system designers and for the extrusion companies, we use the sections on the very left there. Oops, wrong button. On the very right, we use this very complex cross section of our, let's say, profile, where you can see all the details on the small radii. And then for our, like at one point we realized that for our production we don't need it this complicated. This one, no way, come on. So this thing here is enough for our production, and the amount of data that goes into these two sections is a magnitude of one order of magnitude smaller. That means the green one there is only 1/10 of the content of the one on the right. That also means that if we model with the green one, then our models in the computer can be 10 times larger than the full detail model that we don't even need for the production. And then again, for the architect, it's completely perfect to work with this level here. So the middle, the second black one there, whereas again, one order of magnitude smaller. So this is a very big difference. And one thing I can also say for the BIM modeling, we cannot just give the architect our production model, because in Revit it's impossible to open, and they cannot handle it at all. We cannot handle it at all. We have to split down our models into distinct parts. So yeah, the question is to find the right balance. What is just the right amount of information, not too much, not too little, for all our processes, for the architect, for the client, and for the production. So everybody needs a specific level of detail. Okay, and at the core, it's actually not really complicated. We take 2D drawings and we extrude them into 3D, and then we want to hit the right balance. For the machines, we want to generate this kind of detail, so the machines then can analyze automatically all these little machinings that we put in the 3D model, and they will choose the right tools, the correct tools to do the cuts and to do all the notches and everything that's necessary. And then everything has to come together somehow in the 3D model to replicate the realistic shape at each part. Good. And then from there, it can get more complicated. My point in this part of the presentation is all the pictures that you have seen, like the previous picture and this picture, is not made with any parametric modeling software. It's not done with CATIA, not done with Inventor, but with this Rhino software that we use for a couple of years now. And the interesting thing about Rhino is it is very, very small and very, very lightweight compared to the original traditional software. And it looks a little bit stupid sometimes, but it's a misunderstanding. It is just very simple software that is super capable, and it can be automated very well. So it is not able of any parametric modeling, but because we can automate it, and it has a powerful automation software with it, automation interface with it, we can get more out of it than we ever could do with CATIA or with Inventor. And this is the new thing, and also the core of my presentation pretty much, how we experience this shift away from parametric modeling to arrive at, you could say, at a better stage of parametric modeling. So it all comes back, of course, to parametric modeling. We just don't use the traditional parametric modeling software anymore. We have a more powerful system that by itself cannot even do parametric modeling. I don't know whether that makes sense, but let me keep going. Maybe everything becomes more clear. So what we see here now is a very bespoke. You cannot do that with parametric modeling at all. You have to go in and you have to really figure out one by one where does each part go. And you can only, like until now, we can only do that with our brain. Parametric modeling would not help. So here you can see also a hybrid. So some parts of this were generated with parametric, with Grasshopper in this case, which is this Rhino system, not parametric, but with a generator. And then we have to go in and clean up a lot, because the generators can only take us so far. In the end, we still have to do a lot of cleanup. But we manage, and we can, without the parametric modeling systems, we can make very complex geometries, of course. Yeah. So this is pretty much the new strategy also now, that we abandon Inventor, we abandon CATIA. These are very old softwares and very complex and very expensive softwares. The new tool and the new paradigm uses very simple software. It's very cheap, and we can automate the hell out of it. And it's also fun to automate and easy to automate, especially with AI coming in. You don't have to program themselves anymore. So we arrive at a stage in 1 year from now or so, you will have a situation where you tell the computer the program and the tool that you need, and it will automatically program it with the new tools. So nobody needs to actually make these digital tools anymore. At the core, the building information modeling means that you have information and geometry, and you bring that all together, as you can see in this picture. So all these individual parts in 3D, they carry information which you can replicate to any database system like Excel or so, and together with all the parametric information and the geometry, you can do amazing things. Yeah, this is just for you real quick how the Grasshopper interface works in Rhino. This is the, let's say, our new way of replacing the parametric modeling. So here you just put commands on top of commands. So you start with the input, which could be a line or something, but some very simple geometry, and then you take it apart. You take the endpoints and you divide that and copy that and offset and so on. So all these individual steps, they do something to the geometry, similar to what parametric modeling was doing. Okay, and now I show you some examples of projects that we did with this new pipeline. In the beginning, this is my personal experience from, let's say, 2013, Tianjin Yaoyaoqi. Some people know it, and I'm very happy to see that it is getting finished now. We started the project with my team, 19,000 unitized curtain wall panels, and we used this parametric modeling software that the company had back at the time, which is based on Inventor. And then over the years, I was in and out of Gartner and working with Rui, for instance, and working for Priedemann with my own office. And we tried to replicate the possibilities of the parametric modeling software with Rhino. And we, step by step, enabled ourselves to do that. And also Rhino got better and better. Grasshopper came along. So on the right side, all the green stuff is actually done in Rhino. The yellow stuff is Grasshopper and generators. We see that more and more now. One project that was very pivotal for us was the Sydney Darling Harbour the Ribbon project, where we were responsible for the 2,900 aluminum cladding elements. They're all parametric as well. Nothing is 90 degree again, so we have these Grasshopper generators, several of them, and then a lot of work to clean them up. The interesting part is that we have a flat frame unitized system, and then on top of the flat frame we have a twisted metal sheet geometry. So getting that right is quite a lot of effort. And here you can see in the middle part it's quite repeating, so we can use some generator. But on the edge here, we cannot use generator at all, and this is where the parametric modeling software is usually completely failing. Because you would not go in and parameterize any of that. You have to develop it. You have to try 10 times to get it once right. Yeah, there's a lot of back and forth between the engineers and the facade designers and so on, and the 3D modeling team. One project that we did at Gartner just recently is not the church, not the Sagrada Familia in Barcelona. If you ever went to Europe, then you may have seen it. It's from Antoni Gaudi in Barcelona. Very impressive, highest church project in Europe, and only recently they push for finalization of the project in a couple of years from now. What we did was actually only the cross on top of it, so only the smallest part on the highest tower. So you can walk inside, and it's a high performance concrete structure covered with some tiles and all made of stainless steel with reinforcement bars and so on. And our team did the 3D geometry with Rhino and Grasshopper, and again, no parametric software used. Very cheap setup, very simple tools, just automated a lot. We automated it with Grasshopper and with our own tools. Yeah, and it's getting quite complex. And we build that as well. So our factory also built the steel frame and developed all the technologies to bring it together. It's actually these 4 arms, one top arm. So we have 5 of these relatively similar structures, and the center thing, as well as the Fust, we call it the stem of the cross. So you have these, what is it, 4, 5, 6 parts, and the nucleus, the part in the center. And then, okay, so we do this for a couple of years now. Whenever we have very highly complex designs, same as Zaha Hadid and so on, then we have to use Rhino because there's no other way actually. So we are far beyond the limitations of the parametric modeling software. So it turned out over the last 10 years that Rhino is the right software to approach these very complex geometries. That led us to the question whether or not we can use all the things that we learned on this highly complex project on the more simple projects. And how can we do that? So for this project here, this is number 1 Liverpool Street in London. We used it a little bit. Most of the facade was made with a traditional parametric modeling software. And for this complex part here, we then started using Rhino. and it was very helpful there. So the story is that on this facade you have these areas here where you have aluminum casts. These casts have complex geometry shape. This is from the inside. On the outside it's the same. You can see it here a little. No, buttons. You can see it here a little bit. So inside and outside have this very intricate pattern, and you cannot really do that with parametric modeling software again. It's getting too complicated, everything. And we have good teams actually. We have a very good parametric modeling team in the office, and they say it's just getting too complicated for us. I'm sorry. Do you have a better way? And then our team can actually deliver. And this one also a project that we did in Rhino, and it was a very simple project that we did not use any of these automation tools. We just used copy and paste like in the olden days, and pulled together different machining operations into a variation of facade elements. Yeah, you can see it here. So we built ourselves a little good workshop here where we provide a library of different machinings and operations, and then we just put it together the way we need it in a very simplistic way. And also Rhino again is a very good software for that. And here also this is also another situation where it shines, where you have these curving parts. And now I come back to that maybe almost a little bit boring point now. In parametric modeling, we have limitations when we use traditional parametric modeling software. Rhino is not a parametric modeling software, but because we can automate it, we can do even better parametric modeling. So that is also why I cannot really just say the end of parametric modeling as the title of the presentation, because it's actually the beginning of parametric modeling. We overcome the limitations of the original software. This is one that also just opened. I was involved like many years ago. This is a Beijing Sanlitun Louis Vuitton store where Gartner Retail Hong Kong just finished this with Jun Aoki, architect in Sanlitun. And in the beginning it was supposed to be aluminum extrusions as the screen, and I developed the modeling system that we use there. Again, with parametric modeling software you cannot do anything, but you have to automate Rhino. Okay, and this is one project that we have now. I cannot talk about it much. We have to produce 16 kilometers of these bent steel frames, and we still look for a supplier who can help us with this, to do this in an efficient way. We try in our own factory, already did a mock-up of this thing, and it's really quite tough to get it all built. And it will be a very wasteful process unless we can, together with some good partner, innovate the hell out of it and find ways to do this in a much more efficient way. Yeah, glass, of course, very interesting. Yeah. So we talk about simplification of a process here. And in the office we also wonder how can we put these new possibilities into a proper framework so that we enable ourselves to have every project benefit from our findings. At the end of the day, it's very simple what we do. We get from the architect some kind of model, and we will also create some sections from it, derive some sections from it. We will develop a system design and develop the architect's model into a proper wireframe model. If we bring this together, we can make a 3D model from it and send it to the production. And this process is always the same, no matter of the complexity. Simple projects, complex projects, it always works like this. And also independent of the software, that this is what we found, that it always stays the same. So yeah, we thought about that, and we tried to rationalize the process into distinct steps, and that led also us to make an experiment. Maybe if you can start the I cannot really do anything. Yeah, they have to hit a button, Juhoi. So what's happening here is we make a thought experiment. No, we made a thought experiment whether or not we will be able to come up with a system that completely automatically creates the 3D geometry just from sections. Just from sections. So in facade design, we always have 2D system design, which you can see on the screen right here. Cannot? Okay, never mind. So I explain it to you. We have the 2D sections. We would also give a 3D model like the wireframe, which is a very simplistic 3D model. And if we link this together in a correct way, then we can push a button and all the 2D elements can be extruded in the correct position in the 3D. And also all the machinings that we have to do, all the Boolean operations that cut away from the 3D model, we can also put into the 3D automatically from the sections. And so with this idea, we develop a whole system now where we give our users, we have like 100 users right now with Rhino, and we give our users a very simple tool chain that allows them to model very complex things with a very limited and very powerful number of simple commands that can build up the 3D model almost automatically and give the user a lot of possibility to interact with the model, to make changes at each particular step. Okay, and this is also pretty much the end of my presentation. We went through this process coming from CATIA and over Inventor, and now we end up with something very simple that looks like a toy, but it's very, very powerful because it is so simple. And it saves a lot of money. It saves a lot of money as well. That's also important. And we also find in the market many young people who are trained on that software already. They come out of architecture school and out of design school with these skills, and that benefits us a lot. It's very difficult to teach and train people on Inventor and CATIA. It's very expensive. I repeat myself. Rhino is an interesting way forward for us. Many of you will know already, but I can confirm that here a real change in the industry is happening. And that was my presentation.